Okay. So in this video, we will talk about inferences on B0. So as you might guess, well, it will be very, very similar to that of B1. So we will just write B0 minus beta 0 divided by S of B0. It is T-distributed, right? And when we are making hypothesis tests, for example, if you just say H0 beta 0 is equal to 0 versus some other thing, or beta 0 is equal to, let's say, M, right? M, then this will just convert to B0 minus M divided by S of B0. Okay, let's see. So this statistic B0 minus beta 0 divided by S of B0, well, it again has the t-distribution with n minus 2 degrees of freedom. Why? Remember again, B1 and B0, we can show that they are normally distributed. Okay, they are normally distributed, right? Hence, since they are normally distributed, their expected value divided by their estimate of standard deviation has a t-distribution, okay, with how many? With n minus 2 degrees of freedom. Hence, just similar to beta 1, we can construct a confidence interval. Remember how we did for beta 1, it was T alpha over 2 times S of B1, right? We have exactly the same thing here, B1, sorry, minus T alpha over 2 times S of B1. Okay? So in practice, these calculations are done by just computer software. Okay, you can just use Excel or MINITAB, or in fact, we are using R. So they're just calculated by the softwares. So let's find a 95% confidence interval for beta 0. So again, what we need at first is find S of B0. From the formulas, just plug in the values. It turns out that S of B0 is 1.7684. So remember, S of B1, it was equal to 0.05, right? So this is, if you just compare this, it's practically very, S of B1 was very small when you just compare it with S of B0. So it just we can say this, the effect of this in the confidence interval. The confidence interval for beta 1 was 0.8 and 1.01. So it was 0. Almost the range between the left part and the right part is almost 0.2, but it's greater than 7 in these beta 0. Okay. So a 95% confidence interval for beta 0 is given by this equation. So as I said, the confidence interval for beta 0 is practically very large. Okay? It's wide when you just compare it to beta 1. But why is that? So let me just try to make an intuition on this. So let's say I have the data like this, right? And say this is the regression line, okay? So here, beta 1 is the slope, okay, here, and beta 0 is the intercept there, okay? So for given this red set of data, this is my regression line. So assume you have another set of data, okay, let's say it's green, right? Then you have a regression line just like this, okay, just like this. So it turns out that, well, beta 1, which is the slope of this line, okay, beta 1, the slope of this line, well, it changes with the new set of data. But as you can see, its change when you just compare it with beta 0 is smaller, okay, because, well, the center of the data, which is here, does not change too much. Hence, the slope of the line does not change too much. But if you just think of this as a, let's say, tahterevalli, okay, the center of the parts which are close to the center does not move too much. But the parts at the end of this tahterevalli, okay, this part. So here I have it. I have the definition of this, which is the intercept. Okay? So this part changes a lot. That's why the confidence interval generally regarding beta 0 is wider than that of B1. Okay, so if you're just making the hypothesis beta 0 is equal to k, then again, this is my test statistic, okay, t, b0 minus k, okay, b0 minus k, divided by S of B0. Well, this is my T observed, okay? Then just compare it with T alpha or T alpha over 2, whichever you like. So this is small p, right? Small p is the value, yes, this is the small p. Small p is the value, and large p is the random value. So just test whether beta 0 is equal to 0 versus beta 0 is not equal to 0. Just take alpha equal to 0.05. So this is a two-sided test. In fact, with the same alpha level, I have just found the confidence interval. Remember? So the confidence interval in the previous example, it was a 95% confidence interval. Okay? Just look at here. Well, you can just make the hypothesis test by looking at this confidence interval. So here I have beta 0 is in 0.21, 7.45. Okay, and this is what? This is 95% confidence interval. So since, well, the alpha is the same with here, I can just make the test without, I can just conclude the test without making the test, right? So since 0 is not in the confidence interval, since 0 is not in the confidence interval, you can reject HC, reject HC. So it turns out that the p-value is, so the T observed, so in fact this is T observed, right? And this is small p, sorry for this. So here I have, this is T observed, okay, B0 divided by S of B0, that's equal to 2.17, and the p-value associated with this is equal to, so this is 2.17. Let me just plot this so that this again illustrate how we find the p-value. This is 2.17. Okay, so this is T random variable with V is equal to 31 degrees of freedom. And the area here is 0.019. So the p-value is 2 times 0.019. That's equal to 0.038. Okay, that's my p-value. So what does this mean? Since this p-value is equal to 0, smaller than 0.05, we just reject H0 and conclude that, well, beta 0 is not 0. Right? So as I said, we will use, generally in real life, we don't calculate them with our hands. What we do is we just use the softwares. So I will just show you outputs of 3 different softwares. The first one is Excel, okay? So if you just look at this, well, we will see, we will talk about this an hour later, and we will talk about this table later. But what you can see is, well, this is the number of observations, 33, and okay, let's look at here. Okay, just focus on this table. Okay, so here you see that, well, we have 2 lines. The first one is the intercept, which is related to beta 0, and the second one is related to beta 1. Okay, it turns out that, well, it just gives the estimates. Okay, so these are B0 and B1. Okay, so the second line, you can not see this, but this is standard error. Okay, so this is what? This is S of B1, and this is, sorry, this is S of B0, and this is S of B1. Okay, and this is the T statistics and P value. So what is T statistic and what is P value? Well, so what does this mean? It means that, well, you have a hypothesis here, okay? So there's a hypothesis associated with this, let's say, this row, okay? And there's a hypothesis associated with this row, okay? So you have some hypothesis. So this refers to some hypothesis test. But what kind of a test? So if you just look at this, you can remember, this is 2.17. So what we are doing is, well, this is T observed. T observed is equal to B1 divided by S of B1, okay, which is equal to, what is B1? B1 is 3.83 divided by what is S of B1? Sorry, this is B0, right? So this is B0, sorry. This is B0. And this is S of B0. So what is B0? B0 is 3.83. What is S of B0? That's 1.77. So remember, it was something like this, B0 minus beta 0, which comes from the hypothesis. But so B0 minus beta 0 divided by S of B0. So this first row refers to a hypothesis test where you have B0, you are just testing, in fact, H0, beta 0 is equal to 0 or not, okay? Versus B0 is not equal to 0, okay? Well, as we said, this beta 0 equal to 0 and beta 1 equal to 0, these are important tests. So therefore, the statistical packages, by default, they just give the t-statistics and p-values of these hypotheses. Okay? So in fact, let's recap. So this one, 2.17, is the t observed for what? For this hypothesis. Okay? So b0 minus beta 0, and beta 0 just comes from the hypothesis as 0. So this is b0 divided by s of b0, 3.83 divided by 1.77, and that's 2.17. And what is the p-value? Remember, the p-value is 2 times probability that t is greater than 2.17. Okay, that's the same thing that we have found here. That's the p-value. And this is, okay, this is equal to 0.04. That's because we have 2 digits after the decimal point, right? And look at here, again, this is the t-statistic. This is t-statistics of what? H0 beta 1 equal to 0, right? Versus H1 beta 1, so beta 1 is not equal to 0. Okay? So the t-stats, or the t-observed, that's equal to what? B1 minus 0 divided by S of B1. And that's equal to what? 0.90 divided by 0.05. And that's equal to 18. Okay? 18.03, because, well, there are some numbers here that we don't know. Okay? And the p-value, associated p-value is 0. It's almost 0. And hence, by just looking at this, you can say that, well, uh, this hypothesis is rejected, and this hypothesis is rejected. Okay, so we can say that, well, beta 0 is not 0, and beta 1 is not 0. Okay. And how about this? This is the confidence interval. You can see that, well, this is the same confidence interval we have here. Okay, that's not a big deal. So why we have two same confidence intervals? Because Excel just gives you by default a 95% confidence interval. So in the second part, it gives a confidence interval that you just ask for. So I just give a 95% confidence interval again, hence that's what we have. So if you just ask Excel, give a 90% confidence interval, then it will first give this is default, then it will give a 90% confidence interval. So just look at the 95% confidence intervals here. Well, they are equal to 0.92, 22, and 77.44. And this is exactly the same thing that we have found in the previous slide, right? Not in the previous, but two previous slides. See, 0.21, 7.45. Yeah, almost. Okay. And this is 0.80 and 1.01. That's the thing that we have found for beta 1. Okay, these are the confidence intervals that we have found beta 1. Well, this is the R printout. Okay, so in fact, I have the same thing here. The first row associated with beta 0. The second row is associated with beta 1. So these are the estimated, the estimate values. So these are B0 and B1. And these are the standard errors, which is S of B0, and this is S of B1, okay? How about this? This is the T observed, right? This is the T observed for what? For beta 0 is equal to 0, and this is the T observed for what? For beta 1 equal to 0. Okay, so for this hypothesis. And again, these are the T values. Sorry, these are the P values. As you see, this is 0.0382. This is exactly the same thing that we have found. Okay. See this 0.038, right? 0.038 just here. And this is practically 0, that's smaller than 2. So this is equal to 10 to the power minus 16. Okay? 2 times 10 to the power minus 16. So these are the significance codes. Okay, so R puts some stars or these dots, okay, to show you that, well, this p-value or this to observe is significant or not. So it says that, well, between 0 and 0.001, so what does it mean? If your p-value is smaller than 0.001, you will see 3 stars. Okay, you see you have 3 stars. If your p-value is between 0.01 and 0.001, then you will have 2 stars. I don't have any 2 stars there. If the p-value is between 0.01 and 0.05, you will see a star there. Okay, so I'm just seeing a star here because it's between 0.05 and 0.01. And if your p-value is between 0.05 and 0.10, let's say, then you will see a dot. So as we say, well, generally, people tend to reject the hypothesis of your p-value is smaller than 0.05. Well, between 0.05 and 0.10, well, you may reject this, but the general tendency is to get more data. But if you have any question, then, well, you may just reject this if you're not given any alphabet. And between 0.1 and 1, you don't see anything just next to your p-value. Okay? So again, we will discuss on this, okay? We will discuss what we have in terms of this table, okay? In the next slides. And this is a MINITAB printout for the same exam, okay? The MINITAB printout. As you see again, this is the row associated with beta 0, and this is the row associated with beta 1. And again, this is S of P0, and this is S of P1. This is the T observed values, okay, the T observed values, and these are the P values associated with them, okay? As you see, this is exactly the same thing that we have. And this is the ANOVA table, okay? This is the ANOVA table. This is the same table with the one that we see in the Excel, okay, here. This is the same thing that we have here. We will discuss on this in the next slides. And this S, R squared adjusted, these are the same values that we see where in this table in Excel, okay? R squared adjusted, right? And here. And in fact, we see them here as well. This is multiple R squared adjusted, and so on and so forth.